Okay, welcome back to Mr. Hassan's Maths channel. I'm now going to be answering question number 9 from the International A-Level Edexcel Pure Mathematics P4 January 2021 session. Now this question here is about volumes of revolution. We're given a sketch of the part of the curve with parametric equations x equals tan theta and y equals 2 sine 2 theta. So it's a parametric equation, meaning it's been given in terms of a third parameter. It's not y equals some function of x, rather it is x and y both in terms of a third parameter theta, which defines the curve. We're told that theta is greater than or equal to 0. It says the finite region shown shaded in figure 3, which is between 0 and x equals √3, and the curve. It's bounded between the curve, the x-axis, and between the line x equals √3. The region is rotated through 2 pi about the x-axis to form a solid of revolution. Show that the exact volume of this solid of revolution is given by this formula, and you've got the integral between 0 and k of p times 1 minus cosine 2 theta with respect to theta, where p and k are constants to be found. Okay, so I'm going to deal with this question now. Okay, I've just taken like a screenshot or little picture of the diagram and the information on the next page, so I have enough space. Basically what we have to do is we have to take this shaded area and we have to rotate it 360 degrees around the x-axis. It's like wrapping around the x-axis. It becomes three-dimensional now. Okay, now what I'm going to do is I'm going to make it clearer to you, I'm going to just show you a little animation that might make you understand it better. Okay, so here we have a region which is shaded between the points, say A and the point B, x equals A and x equals B. This is the area underneath the curve. So what we have to do is we have to basically, this is of course not the same as that, this is just like an animation to show. Well, basically what we have to do is we have to rotate this 360 degrees around the x-axis to form a three-dimensional figure. So something like this. Okay, it's going to just rotate around. It's like wrapping around the x-axis, and you form this three-dimensional figure like this. Now in this figure here, this line is like, it's like this becomes like a circle. You see the end of this and the end of that. They're like circles, right? Wrapping around the x-axis at the front and the back. So you can think about these as tiny little cylinders, okay, which are going from the beginning to the end of the shape, and these cylinders have a radius r as follows. So like we've now just taken just a slice of this whole area. So what we've done is, as I said, we rotated this around. So it's like you're rotating a little cylinder around the x-axis. Okay, now this little cylinder has a radius of r. Say it's so thin that this side and that side are exactly the same. Such a small, thin, tiny little cylinder. So you have this is r. This distance here is r, and this is just a small amount along x, which is we call dx, a small amount along x. And we got to find the sum of all of these little, so basically if you find the area of the cylinder, the area of a cylinder is pi times r squared times h. So the cylinder here has a radius r, and its height is like this distance between these two discs, so it's going to be like dx. So it's pi times y squared, because this is like a y value there, pi times y squared times dx. All right, that's the area of this little cylinder. But we've got to find the sum of all of those cylinders from A to B. That's what we've got to do. So if I just take that little shape here, so as I'm saying, we've got like this, this is like the radius, you could say. Okay, this is like the radius. Okay, and this is like the height. This is like the height. So the radius is y, and this height of the cylinder is dx, a small amount along the x-axis. So we know the volume of a cylinder. The volume of a cylinder is given by pi times r squared times h. So in this case, you got pi times the radius, which is basically y squared dx. And we want to find the sum of all the cylinders from the beginning to the end. Sum all of them up together. So basically what is, this is, remember, a and this is b. If we find the integral of this between the limits a and b, we will then find the volume of each of these cylinders and add them all together. That's what we're basically doing when we do this. Okay, so we're basically finding the volume. Let me write that in a neater way. So what we're doing here is we're going to have, so basically we're saying we're finding the volume between the limits of b and a of pi times, instead of r, I'm going to write y, because that all of these values are the y values there, y squared, and instead of h, I'm going to write dx. Okay, so we're basically making the sum of all of those cylinders from A to B. So this is the formula that we're going to use when dealing with such a problem. Okay, so now, let me just get rid of this now. We got to kind of refer it to this. Let me just get rid of all of these things. Okay, so now we have here our thing that we need to find the area or the volume of revolution. Okay, so now our objective therefore is to find, this is the volume. So our objective is to find the volume, which I'm going to write as pi. Then I'll put the integral, because pi is a constant. You can write it out here, it's no problem. It just makes life a bit easier. Y squared dx. That's our objective. Okay, so just like a little introduction into how this formula comes about. You should know this formula without having to go through all of that. I just wanted to explain for some of the students maybe who don't know where this formula comes from. Okay, it's always good to have an idea of what the basis of something is, rather than just to memorize something without understanding. So right, that's how you find the volume. Just memorize this formula. Okay, so now the problem we have now is we don't have a formula for y in terms of x. If you want to integrate y squared with respect to x, we've got to have y squared in terms of x. We don't have y squared in terms of x. Now we could try to express y in terms of x by changing this into a Cartesian form, but normally that's something which takes up more effort than doing another little trick, which is using the kind of like using, similar to how we differentiate parametric equations, kind of like using the chain rule. Okay, so what I'm going to do here is I'm going to show you how we're going to deal with this. Okay, I've got all the information here that I need. Yep, okay. So what I'm going to do is I'm going to do the following. I'm going to say this is the same thing as saying pi times the integral between, now I'm going to put here theta 1 and theta 2, okay, of y squared dx d theta d theta. This is like the chain rule in a way, because the dx d theta times d theta will give you dx. So I've put d theta here, so the limits now have to change to thetas, not in terms of x. This is in terms of x. Okay, they have to be in terms of theta now. And I have to replace y with whatever y squared is, and I have to replace dx d theta with whatever d theta is. So there's a few things I have to do first. One, I have to change the limits. So I'm going to go to the limits first and change the limits. Okay, so I want to find what theta is. When the x values here are 0 and root 3. Those are the x values here. So I know that x equals tan theta. Therefore, I know that theta equals inverse tan of x. So when x equals 0, theta equals 0. And when x equals the square root of 3, theta equals, now we want to do it in terms of radians. Okay, whenever you use differentiation and integration with trig functions, you must always use radians, always. Okay, so we're going to have root 3. We can put our calculator if you want to, that's fine. I'm just going to do this. This is root 3, this is 2, this is 1. So the tan of this angle is root 3 over 1. This is 60 degrees. That's pi over 3. So this is going to be pi over 3. So our limits have become 0 and pi over 3. So we had first 0 and root 3. Okay, now it's become the 0 stays as 0 and the root 3 becomes pi over 3 in terms of theta. So I've got so far my volume equals, I have my limits now as from 0 to pi over 3. That's the first thing. Okay, next thing I want to do is to find out what dx d theta is. Okay, I know x equals tan theta. Now if I differentiate x with respect to theta, now we know one of the results we know is that differential of tan theta is sec squared theta. That's one of the results that we should know, and it's also in the formula book. It's very it's there very clearly written, so it's something you can just quote straight away. So tan theta, its differential is sec squared theta. So now I need to write what y squared is. Now y is equal to 2 sine 2 theta. So I'm going to take the y, which is 2 sine 2 theta. So I'm replacing the y with that squared. Okay. In fact, what I'm going to do to make it clearer, just to make it clearer for everybody, I'm just going to write this first down. I'll say, so the volume is equal to pi times, I've got theta 1 and theta 2, which is now pi over 3 and 0. I've got y squared dx d theta, right? So now I'm going to say, okay, I know what these things are. I know what y squared is. Y squared is 2 sine 2 theta all squared. So I'm going to write this first, 2 sine 2 theta squared. And dx d theta I know is sec squared theta. So I'll write here sec squared theta d theta. Okay, so now we've now got rid of all of the x's and everything is in terms of thetas. So we're almost got there. Now we have to just manipulate this to make it look like what they want us to make it look like. So if you look to see what they want us to make it look like, we want to have 1 minus cosine 2 theta d theta. All right, so now what I'm going to do here, because this is a single angle and this is a double angle, all right, and I have to, even though the answer is going to be a double angle form, all right, I'm going to make them all into single angles because then I can simplify it. Because this is like right now 1 over cosine squared theta. I guess I could do something like that as well. Let me try both ways. Let me deal with this in both ways. First, let's expand this. We'll say this is going to be 2 squared, which is 4. All right, so this will be 4 times sine 2 theta. Okay, so you're going to have, I'm take the 4 outside, so I'll have 4 pi. I'll have sine squared 2 theta over, now sec squared theta is the same as 1 over cosine squared theta. So I'll write this as cosine squared theta. Okay. Now, yeah, so what I can do here now, okay, I think it will be easier for me actually to change this really, because I could try to make this into a double angle, but I think that's going to be more complicated. I think easy thing is to change this. I know that there's one of my identities that we learn is sine 2 theta equals 2 sine theta cosine theta. That's one of my identities that we know. So if I change this, this is going to be like 4 pi times the integral between 0 and pi over 3. Now sine squared 2 theta is the same as 2 sine theta cosine theta squared divided by cosine squared theta, and we want to integrate that with respect to theta. So that's going to give me now 4 pi times between 0 and pi over 3. This is going to give me 4 sine squared theta cosine squared theta divided by cosine squared theta and integrate with respect to theta. Now what's going to happen here is these are going to cancel out. All right, and that 4 I can multiply with what's outside. So this gives me 16 pi between 0 and pi over 3. And here I'm going to have sine squared theta d theta. Now, to integrate the sine squared of theta, we have to rewrite it in form of the double angle. That's how this is going to arise now. Okay, we should know that. We should know that to integrate sine squared theta, we have to use the identity, because we can't integrate it when it's got squared, because you're going to have a function inside a function. You have like sine theta inside the squared function, so you have to add 1 to the power divided by the power. You have to have, when you start, the differential of what's out inside the function out here. So it has to be multiplied by cosine theta for you to be able to integrate it the way it is here. So you cannot integrate it this way. So what we need to do is we need to change this into a form that we can integrate. Now, one of our identities that we should know, very important identity, is basically cosine squared theta is equal to, cosine 2 theta, okay, double angle formulae. There's one for sine 2 theta, which we already used in this part here, where we changed that. All right, from this was sine 2 theta, became 2 sine theta cosine theta. The other one is for cosine 2 theta, which again we have to know. These are not given to you in the formula book. Neither of these two are. They're based on the formulae, which is like sine A plus B and cosine A plus B. That's what they're based on, which are in the formula book. And if you change the A and the B both for theta, you'll get this formula. And if you change the A and the B both for theta in the formula, you'll end up with cosine 2 theta, and it'll be easy to derive it. But you should know this by now, that cosine 2 theta is cosine squared theta minus sine squared theta. At least that much you should know. And if you want to find what sine squared theta is, I want to express sine squared theta, I'm going to change this cosine squared theta into 1 minus sine squared theta. So this gives me cosine 2 theta equals 1 minus 2 sine squared theta. Okay, that's the identity that we need to change this into the form that's required with cosine 2 theta. If I make sine squared theta the subject, well, I'll have on this side 2 sine squared theta, 1 minus cosine 2 theta, and then I have to divide by 2. So I end up with sine squared theta is equal to 1 minus cosine 2 theta over 2. So that means I can replace the sine squared theta with 1 minus cosine 2 theta over 2. Or you could say a half times 1 minus cosine 2 theta. And then it comes into the form that we require. So I'm just going to take this and bring it down here so we can have it in front of us to see exactly the form that we need. Okay, so we need this form here. Okay, that's how we need to put it in the end. So I'll just put this down here so we can see it. Okay, so now what I can do is I can take this, I can say this means that I've got 16 pi, and I've got the integral between 0 and pi over 3, and I've got a half times 1 minus cosine 2 theta, and I got to integrate that with respect to theta. So you can see it's almost done now. Okay, so to express it in the way they want everything inside. So inside, I'll just put it, I'll put the 16 pi back inside. That's pi over 3 and 0. A half of 16 pi is 8 pi. So it's 8 pi, 1 minus cosine 2 theta with respect to theta. And I think that is exactly that's what they want in this form. And they told us where. Let's go back to the actual question. Okay, where P and K are constants to be found. Okay, it just says constants to be found. All right, that's fine. So where P and K are constants to be found, now you can see that P is 8 pi. So we can say therefore P is 8 pi and K is pi over 3. Okay, so there we have the answer to part A. They didn't tell us to integrate yet. They just said to basically show that it's in this form. Now part B, I'm sure they'll say integrate it. Okay, so we end up with this. Let me just take this to the other side so we can see what we have. Okay, so now they've said, hence find by algebraic integration the exact volume of this solid of revolution. So we have this now ready to integrate. So we're going to put, I like to take this outside, constant. So I'll have this between 0 and pi over 3. And I'm going to integrate 1 minus cosine 2 theta with respect to theta. Now it's very simple to integrate this now because everything is ready and easy to integrate. So I'll have 8 pi times. Now this is going to be if you integrate 1 with respect to theta, you get theta. If you integrate cosine 2 theta with respect to theta, well, first of all, the integral of, this is like cosine of something. This is like integral of the cosine of something is going to be the sine of that same thing. It will be positive sine of the same thing. So this stays negative. You have sine of 2 theta, but then you divide by the differential of what's inside the function, which is 2. Okay, and that is that, and the limits are between pi and pi over 3 and 0. Simple as that. So now we have to just substitute those values in. So we've got 8 pi. Now we're going to have pi over 3 minus the sine of 2 times pi over 3, which is pi over, well, that is 2 pi over 3. Okay, divided by 2. And we're going to have minus, you're going to have 0 minus the sine of 0 over 2, which is 0. So it's going to just be minus 0, basically. Okay, so now you should always make sure first, because if that was a cosine, for example, here, then that's going to become, you know, if it was a cosine that you put the 0 into, it's going to become 1. Cosine of 0 is 1. So always check first. Don't just think there's a 0 here, so the second bracket will always be 0. That's not true, especially when you've got e power of something and cosine of something. So be very, very careful about that. Now, the sine of 2 pi over 3, it gives you the same value as the sine of pi over 3, which is going to be, if you can just use your calculator for that, it's no problem. The sine of pi over 3 is like the sine of 60 degrees, so it's root 3 over 2. So let's just have a look. The sine of 2 pi over 3. 2 pi divided by 3 gives root 3 over 2. I was right. So you've got 8 pi. You have 8 pi times pi over 3 minus, and you got a half of root 3 over 2, which is root 3 over 4. This is root 3 over 2 divided by 2. So you're going to get this. So let's just now say 8 pi, and this is going to be over 12. That's like 4 pi over 12 minus, this is going to be over 12. This is like 4 times root 3. 3 times root 3 over 12. Okay, because 3 over 12 is a quarter, so it's 3 times root 3 over 12. So we end up with 8 pi times 4 pi minus 3 root 3 over 12. And so now what we can do is we can cancel out some of the common factor. Here we've got 8 and 12. So we're going to have here the 8 cancelling with the 12. You can see 4 goes into both of them, so that's going to be a 2 here and a 3 here. So you're left with 2 pi outside the bracket, and inside the bracket you've got 4 pi minus 3 root 3 over 3. I'm guessing you could leave it like that, or we could basically express it separately as separate terms. So you could write this as 2 pi over 3 times 4 pi minus 3 root 3. I'm sure each of these would be perfectly acceptable ways of expressing your answer. Okay, but if they want it as separate terms, in fact, let's see how they asked for the answer. They didn't. I don't think they asked for any particular way. So this would be correct. You could write this as your answer. You could write this as your answer. You could also write them as separate terms. We have 8 pi squared over 3. 8 pi squared over 3 minus, and if you multiply that, you're going to cancel out the 3. You're left with 2 pi times root 3. Okay, so each of these are all cubed units because it's a volume. So there we have, you can write it in any of these 3 ways. Okay, all of them will be correct. Okay, this one, that one. They didn't tell us in any particular form or which particular form they want us to express our answer. So any one of those 3 forms should be fine. Sometimes they give you like as separate terms. Say, you know, in the form of A plus B, something, whatever. So you have to do it according to the form that they ask you. But here, either of these are fine. Okay, so that concludes this question number 9, which is all about integration, volumes of revolution, and how to integrate trig functions, and specifically sine squared theta. Now we have to, if you'd like to see other questions from this paper, which is the January 2021 P4, you can click on the link that should appear over at the top here, the playlist. Then there'll be another link for a playlist which takes you to integration of P4. Another link here will take you to subscribe to my channel if you haven't done so already. And on top of the page you've got a card which will take you to another P4 paper you might want to watch. Thank you for watching and see you soon.